The topic for this lecture and last lecture were interpolants, so functions that go through a set of data points and go through it in some kind of way that is nice. And as soon as our metric, our quality measure is niceness, you can imagine that there's going to be some debate, some pros and cons, lots of choices that are nice in some contexts, but maybe not quite perfect for others. And so that's why we have some choices. More choices in this particular 2-lecture section than we have in a whole bunch of other ones. All right. One of the things we tried in terms of building functions is to have a chassis or a model was to use to use polynomials, just a polynomial through data points. And that worked pretty well for small numbers of data points. But when we had data sets that were naturally antagonistic to the way polynomials work or graph, we ran into problems. This is the sample one that we had in the last class. And that kind of graph is what we got when we asked for a, how many points are there? 1, 2, 3, 4, 5, 6, 7 points. If we fit a 6th-degree polynomial to this, that's the kind of shape we would get. And that's just because big-degree polynomials grow either to negative infinity or go to positive infinity really, really fast. We can kind of massage it so they behave themselves at least a little bit in the middle of something. But at the end of the day, they're going to want to go down vertically, and they're also going to be smooth, so we get these weird bounces or wiggles, what we called them last class. All right. Our next approach was to use something we called splines, and these are piecewise cubics. So still in the polynomial family, but we're going to join them together. We're not going to use one single cubic for the whole thing. We're going to use a cubic here, a cubic here, a cubic here, and then we're going to tie them together nicely. All right. And we talked about how that would work in terms of, well, I want it to be, when these things join, I can make cubics are smooth, but when they join, they also have to have these smoothness properties. We saw examples of how that would look if we didn't have those last class. So let's just go back and quickly review how we generate these things. So we're going to take a look in MATLAB and W54, fantastic. So what we're just going to do is do a quick plot here. And I'll put a close all at the top, just so our graphs always appear up on top of our screen. All right. So there's our graph, 4 points, 4 red dots around the thing. And we'd like to add a spline to that. Let's do one check here. Yeah. So the model I think that's most effective, we're going to talk about some variations in a minute or two, but the most effective one is to do this 2-step process, 3-line process, and then space. 0 to 6. All right. If we're going to draw a graph in MATLAB, we need to have a lot of points to draw that graph. If we draw it with 3 or 4 points, we got the jaggy thing that we saw last class, because MATLAB just connects the dots. If you have 4 dots, it looks jaggy. If you have 100 dots, it can look pretty smooth. So that's why we generate this lin space thing. And the 0 to 6 is just coming from where our data was. Our data was 0 to 6, so let's build an interpolant on the same range. And then we say, without even using the XX, let's build a spline that's based on x and y. So data to spline information. And remember, PEP stands for piecewise polynomial. Okay. So we're going to build a piecewise polynomial. So again, think of it as a function, as a kiosk. I've got my data points. I'm going to go to somebody and say, here are my data. Build me this mysterious cubic piecewise polynomial thing for me. And it goes ahead and does it. It gives you the information back about those polynomial pieces. Then we would say, I'd like to draw those pieces. So it's a separate operation. And here, we're going to do something that's related to the PP for piecewise polynomial. Evaluate it for me. So I've got it's like having the formula, it's PP sort of, but someone can take that formula and some x's. So notice we're trying to use the same syntax as MATLAB has in its little help bubble there. And if I give someone, here's 100 x values I'd like you to plot at, and here's a piecewise polynomial I'd like you to plot, they can go ahead and do that and say, oh, here are the y values that you wanted that go with those x values. And then we can plot that as well. We'll do our hold on, and we'll do plot xx against yy. And we get a nice graph. There actually are 100 points being plotted here. We can't see them because they're so fine, but that's what the xx's would be, and the yy's are the matching y coordinates for each of those x values. So that's the from scratch plotting of a spline from some data. Questions or difficulties in anyone trying that at home? Okay, lovely. So that's the key thing. So you should be able to do that operation and sort of understand the pieces. And if you're ever stuck, do keep in mind that you can always look up the help menu, and Spline will give you some options. The pp-val, I think, is the less intuitive thing, but I believe if we scroll down to the things that also help me, there's pp-val listed there. So if you look up splines, you keep that word in your mind, the help menu will tell you, oh yeah, there's something that goes with that. pp-val would be its complementary evaluation tool. All right. So that's the basics of splines. We're not going to talk too much about them today, except to maybe digest a little bit what they mean. Oh, I forgot one thing. My apologies. I wanted to add some end slopes to this. So let me just run this again. And notice the slope here is negative, and it's negative at the far end. I would like to tweak that a little bit because I see these guys being almost in line with each other, but going up. So from last class, does anyone recollect how I tweaked this spline command to get slopes? To set the slope at the beginning and the slope at the end. What do you do in the code? Square brackets and slopes around the y. Exactly. So here's your y value. We're going to put 0.5, I think I said was the first slope we wanted. Yep. And then -1 slope at the end. So square brackets, a -1, sorry. First slope, the y data points, and then the -1. Let's try that first. There we go. So whether you like this better or not, it's an alternative. The slope at the beginning is 0.5, so it's a little steeper than the actual connection there. The slope at the end is -1. And we can choose those slopes to be whatever we like. If we don't like this, if we want it maybe looking smoother, maybe we could set our initial slope to something like 0.2. And maybe that would look prettier. Not a lot prettier. Maybe set it to 0. Yeah, that might look a little nicer there. But the key thing is, it's an ingredient you can provide. Person at the kiosk will go quite happily say, oh, you want those slopes and these data points to be fit through? Fantastic. Here's your piecewise polynomial back. OK. What do we get? So to some point, to some limit, at some point you have to recognize there are black boxes around. What I would hope is that we at least have a glimmer as to roughly what's going on inside those black boxes. You might not be able to code it yourself, but you should at least understand roughly what's going on. So here we're going to do a little bit of a dissection of the mysterious thing in the middle of all this, which was that PP. All right. We are going to be building some polynomials. And we're going to be building cubics. So if you look at a cubic polynomial, it'll have 1, 2, 3, 4 numbers that define that cubic polynomial. You tell me the cubic, the quadratic, the constant, linear and constant coefficients, then you know what the function is. I will also bring to your attention that there's this minus xi. Does anyone remember what happens when you put a minus x or minus 5 or something inside the brackets for a function? What does it do to the graph? Shifts it right. Okay. Shifts it in general. This is going to shift things to the start of the interval. So all of these things are going to be relative to, if here's my interval and I had 2 points here, this would be my xi. We're going to be graphing relative to this start of this interval. This is going to be like our new 0. New 0. Mu 0. That's what this shift will do, right shift. It might be a left shift if it's the x coordinate's negative. But that's the idea. And the reason for that is, briefly mentioned last class, we're going to take big powers, right? Cubic's a reasonably sized power. If I had numbers that went out to 1,000 cubed is really, really big. That can be a bit awkward. But if I'm doing things on little intervals, then on each interval, I'm only 100 past the last one. 100 cubes a little smaller, a little more manageable. So what this does, it just makes the numbers roughly on the same scale wherever you are. It doesn't depend on being close to 0 or far away from 0. Not so important, except I'm going to ask you to interpret these functions in a second and on your tests. So that's why I'm bringing this point to bear. All right. So here I call it spline info. Let's just take a look at it. We call it PP here without the caps. PP. There we go. So we looked at this briefly last class. We're going to look at more detail today. If we look at our data points at the very top, x was 0, 2, 4, 6. Notice that we have breaks 0, 2, 4, 6. And pieces, number of pieces, would be how many intervals we have. Going back to the picture. We have 4 data points, so there's one interval here between 0 and 2, one interval here between 2 and 4, and one third interval between 4 and 6. That's what we're going to build our interpolation on. We're going to have 1 cubic for each interval. And this is all being stored in this PP thing. So if someone got handed this PP data, it's called a data structure. That's why it has this little squiggly box thing here. It's not a matrix. It's sort of a collection or a grab bag of various things, one of which is a label called form, one which is a vector called breaks, one is a matrix of coefficients. We'll look at that in a second. And the rest of it is dimension, so it's a one-dimensional function. And the order is 4, or it's a cubic because it has 4 coefficients. So the degree is related to the order. And the idea is this could be used in other applications. So if you wanted a quadratic spline, you could do that. You can do 2D splines with these same data structures. We're only going to use these ones, though. All right. We're going to stick to 1D cubics. However, what we'd like to do is interpret all these things. So the PUP just means piecewise polynomial. The breaks are where we transition from one to the next. The interesting stuff is going to be in the coefficients matrix. So here's how you access that. So first off, if you just type PP on its own, it'll show you the matrix. It'll show you what's inside PP. And it gives you these 6 names here. To access any one of those in particular, you just say PP, then a period, and then whatever it was called. So if it's coefficients, it's coefficients. We can do pp.dim. If you get it spelled wrong, like coefficient spelled wrong, with an extra f or something, it'll say, I don't know what the heck you're talking about, which is perfectly reasonable. So it recognizes those 6 names that were in what it showed you when you just typed pp by itself, and then you can dive in deeper. All right. So we have a 3 by 4 matrix here. What is in this matrix? What single word describes us in this matrix? Let's go for that. All together. Coefficients. It's called the coefs matrix. So it's coefficients, yes. All right. How are they organized? That's the only thing that requires some subtlety. Well, there are 3 intervals. I have 3 cubics running around. Hey, guess what? Each row is a cubic. Hey, I have a cubic. I need 4 coefficients for a cubic. 1, 2, 3, 4. So that you can infer just from knowing where this comes from and what it's describing. The only thing might be, which order are the coefficients in? Does it go constant, linear, quadratic, cubic? Or cubic, quadratic, constant, linear, constant? What do you think? First or second? Second? Why would you think second? I mean, could be either one. You're right, it is the second. When have we ever seen polynomial coefficients before? The roots function, absolutely. We also did it when we fit a polynomial. So we've seen polynomials in MATLAB before, and they always went from highest degree down to lowest degree. So it's going to do the same thing here. That's what it does. So what we can get from this is on the first interval, there's a cubic, and it's going to be this times x minus something cubed, and so on. Let's actually formalize that a little bit. And hold on, are those the same numbers? 0.195. They're different this time. Weird. Okay. Let's use ours. Let's use ours. Control V. Oh, that's a little small. That's a lot small. Can I use to change that? All right. I'll tweak that for you afterwards, but we're just going to put it up here for now. There we go. All right. So the interpretation of this is very straightforward. We need the breaks, and we need the coefficients. because what we're going to do is take this first line here, which is on the interval 0 to 2, 0 to 2, and that means the left break is at 0. xi is 0 for that first one. So our cubic is going to be 0.1008. Oh, I messed with the slopes. That's what happened. The slopes were different. X minus 0 cubed minus 0.1517 x minus 0 squared plus 0x plus 0. That's on the interval 0, 2. On the interval from 2 to 4, we'll do it in a different color here. It's the second row. It applies to the second interval. The left-hand endpoint of that second interval is the 2. And so it's exactly the same idea. Negative 0.1525 x minus 2 cubed plus 0.4533 x minus 2 squared plus 0.6033 x minus 2, that's it, plus 0.2. So it's a very straightforward interpretation of what's going on here. And I do ask for this on tests and exams, so you should be able just to see the process and just recognize the only real gotcha here is, oh yeah, don't forget to subtract the starting point from each of those x's. Questions or comments about that little calculation or interpretation, I guess? It is absolutely. So where do these coefficients come from? They came from the line that said, back here a second, I gave it the data and some slopes, and I got pp back, and I'm looking at pp. So yeah, the spline function is what created these coefficients. So think again, that kiosk, I handed somebody my data, and they gave you back this set of spline coefficients, which is enough to plot the graph.